And the next speaker is Zhongchen Chen, and he's going to be talking about lower bounds for testing graphical models, colorings, and antiferromagnetic Ising models.
Thank you. My name is Zhongchen Chen, so I talk about lower bounds for testing graphical models. And this is joint work with Ivona Bezakova, Antonio Blanca, Daniel Stefankovic, and Eric Vigoda. So we will study the distribution identity testing problem for undirected graphical models. So the problem is roughly as follows. We have a visible graphical model M, and also there's a hidden graphical model M star. And we want to distinguish between the cases that the two models are the same, or that their Gibbs distribution is epsilon far away in total variation distance. So we will focus on one of the most popular graphical model, which is the Ising model. So here's a recap of the definition of Ising model. We have a graph G, and we have two spins, which are plus minus. But in this talk, I'll use the red dot and the blue dot for the two spins. And also beta, the inverse temperature, as a parameter that controls the strength of interactions between the vertices. And the Gibbs distribution of the Ising model is a distribution over all two colorings of the graph. And for every configuration, its probability density is proportional to exponential beta times the number of monochromatic edges. So here's a very specific example of Ising model on a path of 3 vertices. So there will be 8 two colorings, so 8 configurations and their weights. And also Z is the partition function, the normalizing factor. And we can see from definitions that when the beta is positive, the neighboring vertices are more likely to have the same spin. So we call this ferromagnetic or attractive models. And on the other hand, when beta is negative, adjacent vertices are more likely to have opposite spins. So this is antiferromagnetic or repulsive. So we will study the identity testing problem for Ising models. We are given a visible graph G, and also the parameter beta is also given. And also we have a hidden graph G star, and we have sampling axis to the hidden Ising model. And the problem is can we distinguish between the case that the two graphs are the same or the Gibbs distribution are epsilon far away. And we will make the assumption that both the visible and the hidden model have the same parameter beta, and both graphs have maximum degree D. So we make this assumption because that we will show the hardness result for the testing problem, and we only need to consider the simplest case. And for testing Ising model, it's first studied by Daskalakis, Dikala, and Kamas, and in which they gave a polynomial time algorithm for testing Ising model, but their algorithm requires the covariances of the visible model. And one natural way of obtaining the covariance is by using an efficient sampling algorithm for the Gibbs distribution. And it is known that when beta is positive, we have polynomial sampler. This is a result by Jerem and Sinclair. And when beta is negative, it's hard to sample or compute the covariance in general. So that means that in ferromagnetism case, we have efficient testing algorithm. And there's also another closely related but a little bit harder problem, which is the structure learning problem, where we are getting samples from the Gibbs distribution. And our goal is to recover the underlying graph that defines the model. So it's easy to see that when we have efficient learning algorithm, then we have efficient testing, because we can just learn the hidden graph and compare to the visible one. And for learning Ising model, there are many recent works recently in recent year, and here I refer a result by Clivens and Mecca, who gave n square log n and exponential in beta d time algorithm for learning or Ising models. And I want to remark that there is an information theoretic lower bound, which is also exponential in beta d. So this will mean that when the beta d is of order log n, then we have a polynomial time learning algorithm, which means that we have an efficient testing algorithm when beta d is O log n. So to summarize, what we know from previous results is that we have efficient testing algorithm either when it's ferromagnetic or when beta d is small. So the question is what will happen when beta is negative and beta d are large. So in this region of parameter, both sampling and learning are hard. And in fact, we show that for the remaining region of beta, there's no polynomial time testing algorithm unless RP equals NP. So another way of stating our theorem is that if we consider testing antiferromagnetic Ising model, then it is hard in the same region of parameter where the structural learning is also hard. So which is a little surprising because one might think that the learning problem is harder than the testing problem. So I will give a very quick proof outline of our main result. So the key observation is that for the Ising model, when beta is negative infinity, it is essentially uniform random max cut. So that we will use the reduction. This is because the max cut has the fewest number of monochromatic edges. So we will use the reduction from max cut, and we will have a max cut instance. And what we will do is we transform it into the problem of determining if some given cut is a unique max cut or not. So this can be done by adding some extra vertices and weighted edges to H. And if we use this graph as visible graph, and we use the graph by replacing H with an independent set as hidden graph, then basically it shows that testing max cut is hard, which is the extremal case that beta is infinity. And if we want to do finite beta, a lot of more work needs to be done, and we will do by replace every vertex with a random, almost deregular bipartite graph. So in this way, we can simulate large beta and also reduce the degree of the graph. So the same idea is first used by slide to show a hardness of approximate counting. So to summarize, we show hardness of testing antiferro Ising when beta d is omega log n. And also we show some hardness result for testing colorings where we are getting random colorings from a hidden graph. And we show that the testing problem is hard in the same region of parameter where the corresponding learning problem is hard. And also for testing ferro Ising, we give a better algorithm with sample complexity independent of the parameter beta. And the open problem would be, can we find some efficient algorithm in the region of parameter or for any graphical model where the learning and the sampling are hard. And that's all. Thank you.
Any questions for the speaker? Okay, thanks. We'll have the next speaker.